Hello and welcome to Math 135. This is Tracy, and we are going to go ahead and do some problems involving the distribution of the sample mean and the central limit theorem. We are going to identify central limit theorem problems and calculate probabilities involving the sample mean. The central limit theorem. This states that if we take a large enough random sample from a population with mean mu and standard deviation sigma, the sampling distribution of the sample means is approximately normal, no matter what the distribution of the original population is. What this means is that even if we have a population that's some crazy bimodal thing, like you see in the picture, if we took every single member of the population, measured the value of whatever it is we're measuring, and created a histogram, and then made a smooth curve out of it, we get the graph on the left, a population distribution. The x value represents data values for individuals, and the curve gives us probabilities of getting an individual with a certain interval of data values. Now, if we decide on a sample size n, whatever n is, so out of our population, we grab a sample of size n, measure those n people, find the mean, and record that. Throw them back. Grab another sample of size n, measure them all, find the mean, record that mean, throw them back. Then we could create a new distribution, and that distribution would have all of the means with samples of size n in it. So that's the curve that you see on the right. Along the x-axis, what we have is possible values for the mean of a sample of size n. And what happens is that most of the means for our samples cluster around the true mean of the population. And the farther away we get from the true mean of the population, the fewer samples will have that mean. Only a few samples have means that are way above the true population mean. Only a few samples have means that are way below the true population mean. So no matter what our population looks like, if we create a graph that is a smoothed out histogram of the average values for a sample, that graph will be normal, assuming that we have a large enough sample. Well, if the original population is not normally distributed, then we need a sample that's about 30 or above in order for the sampling distribution of the sample means to be normal. If our original population is normally distributed, we actually can say that the sampling distribution of the sample means is normal, no matter how small the sample size. We may have a really high standard error of the mean if our sample size is too small, but we will have a normal distribution for the sample means. The mean of the sample means is the population mean. What that tells us is that our samples will mostly have the same, a mean that is very close to the true population mean. All right, the standard deviation of the sample means, this is also called the standard error of the mean, is not the same as the standard deviation of the population. To find the standard deviation for that normal curve that you see on the right side of the graphs shown, you would take the population standard deviation and divide it by the square root of the sample size. So that's just kind of a recap of the central limit theorem, and now we're going to do some problems with it. Before we do problems with the central limit theorem, though, we need to decide, is this a problem that requires me to use the central limit theorem? A typical central limit theorem problem asks us to find a probability involving the mean of a sample of size n. In addition, we have to know that either the population follows an approximately normal distribution or that our sample size is large enough. if our original population is not normally distributed, then our sample size should be greater than 30 in order to use the stuff that we're going to do. So, is this a central limit theorem problem? A prototype automotive tire has a design life of 38,500 miles with a standard deviation of 2,500 miles. 5 such tires are manufactured and tested. On the assumption that the actual, not just the design, mean and standard deviation are 38,500 miles and 2,500 miles, find the probability that the sample mean will be less than 3,600 miles. Assume the distribution of lifetimes of such tires is normal. So we want to know, is this a central limit theorem problem? So, key thing we're looking for, first of all, are we finding a probability involving a sample mean? If we reread this, find the probability that the sample mean will be less than 3,600 miles. Yes. First key thing, we are dealing with a probability for a sample mean, not an individual tire. The next thing we need to know if we can do this stuff is our original population normal, or is our sample size big enough? Well, our sample size is only size 5, so we need to see in here that the tires have a design life that follows an approximately normal distribution. And that's what the last sentence says. Assume the distribution of lifetimes of such tires is normal. Yes, this is a central limit theorem problem. We are dealing with a sample mean, not an individual tire, and our original population is normally distributed. So here I have highlighted the key information and written down. This is a central limit theorem problem. Next, is this following problem a central limit theorem problem? An automobile battery manufacturer claims that its mid-grade battery has a mean life of 50 months with a standard deviation of 6 months. Suppose the distribution of battery lives for this brand is approximately normal. Assume the manufacturer's claims are true. What is the probability that a randomly selected battery of this type will last less than 48 months? Is this a central limit theorem problem? The first thing we need, breadth doesn't even come into play yet. The first thing we need, are we looking for a probability involving a sample mean? Look at the last question. What is the probability that a randomly selected battery, blah, blah, blah? We are not looking at a probability involving a sample mean. We are looking at a probability involving an individual object. The answer is no. This is not a central limit theorem problem. And there we go. I highlighted the key phrase, what is the probability that a randomly selected battery, not what is the probability that the mean of a sample, blah, blah, blah. No, this is not a central limit theorem problem. How about this one? An automobile battery manufacturer claims that its mid-grade battery has a mean life of 50 months with a standard deviation of 6 months. Suppose the distribution of battery lives for this brand is approximately normal. Assume the manufacturer's claims are true. What is the probability that the mean of a random sample of 36 such batteries will be less than 48 months? Is this a central limit theorem problem? All right, we've got 2 things we need to look for. The first one, are we dealing with the probability of a mean? Well, there it is, the question. What is the probability that the mean of a random sample, blah, blah, blah. All right, this could be a central limit theorem problem. The next thing we need to look for, either our original population is normal or we have a big enough sample. Ooh, suppose the distribution of battery lives is approximately normal. Yes, this is a central limit theorem problem. Even if we had a smaller sample than 36, this would still be a central limit problem. Although our sample size is big enough, 36 is bigger than 30, we wouldn't need to know anything about the distribution of battery lives for this to be a central limit theorem problem. Our sample size is big enough. All right, key phrases highlighted: probability involving a sample mean, and our underlying population is approximately normal, or our sample size is big enough. Yes, this is a central limit theorem problem. All right, how about this one? Suppose that a disease called hypokalemia, I think that's how you pronounce it, is diagnosed when blood potassium levels are below 3.5, I think that's milliequivalents per deciliter. Okay, suppose a patient's measured potassium levels vary daily according to a normal distribution with a mean of 3.8 milliequivalents per deciliter and standard deviation 0.2. If the patient's potassium levels are only measured once, what is the probability that the patient will be misdiagnosed with hypokalemia? Is this a central limit theorem problem? Okay, well, what is the question? If the patient's potassium levels are only measured once, what is the probability, blah, blah, blah? We are looking at a probability of a single thing, not a sample mean. This is not a central limit theorem problem. We are looking at a single thing, one measurement. This is not a central limit theorem problem. How about this one? Suppose that a disease called hypokalemia is diagnosed when blood potassium levels are below 3.5 units. Suppose a patient's measured potassium levels vary daily according to a normal distribution with mean 3.8 units and standard deviation 0.2 units. If the patient's levels are measured on 4 separate days and we find the mean result, what is the probability of a misdiagnosis? Is this a central limit theorem problem? Let's look at the question. If the patient's levels are measured on 4 separate days and we find the mean result, what is the probability? We are looking at the probability of a sample mean. Our sample size is 4. We are taking 4 measurements and finding the mean. Because we're dealing with a probability involving a sample mean, this might be a central limit theorem problem. Now we need to figure out, is our sample size big enough? 4? No, that's not above 30. Too small of a sample size. This will only be a central limit theorem problem if the underlying population, all the patient's measurements, follows a normal distribution. And there it is. A patient's measured potassium levels vary daily according to a normal distribution. Yes, this is a central limit theorem problem. All right, highlighted the key factors. We are looking at a probability involving a sample mean, and the underlying population is indeed normal. If we didn't have a normal distribution for the underlying population, we couldn't do what we're going to do because our sample size of 4 is too small. Okay, how about this one? Oh, actually, we've just got a problem to do here. In 2004, a water taxi sank in Baltimore's Inner Harbor, killing 5 and injuring 16. The safe passenger load for the water taxi was 3,500 pounds. At the time, it was believed that the mean passenger weight was 140 pounds based on data from 1960. Based on that 1960 data, the taxi was allowed to carry 25 passengers. In 2004, it was found that the weights of men in the U.S. were normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Now, average weight for men is closer to 196 pounds and women is closer to 169 pounds. Yikes. Suppose that in 2004, after the accident, the safe limit was set to a maximum of 20 passengers. This assumes an average weight of at most 175 pounds. 20 times 175 gives us that max load of 3,500. All right. Suppose that 20 male passengers boarded in 2004. What is the probability that the mean weight of all 20 male passengers was 175 pounds or more? In other words, what was the probability of overloading the water taxi if 20 men boarded? Because if the average weight of those 20 men was above 175 pounds, 20 times whatever that weight is above 175 is going to give us a total weight of more than 3,500 pounds, a weight higher than the safe limit. So, is this a central limit theorem problem? What is it we're looking for? What is the probability that the mean weight of, yes, this is this could be a central limit theorem problem. The next question we have to ask is, do we either have a large enough sample size, 20, no, or is the underlying distribution normal? Our underlying distribution is weights of men, which is approximately normally distributed. We know that. So yes, this is a central limit theorem problem. All right, we are going to use our TI to find the probability that the mean weight of all 20 passengers was 175 pounds or more. So again, this is exactly the same as our previous normal distribution problems because we have the sampling distribution of the mean, which is a normal distribution. We want to know a probability involving a mean for a sample. And our original population, male weights, is normally distributed. That tells us that if we went out and grabbed a sample of size 20 and found the mean and threw them back and grabbed a sample of size 20 and found the mean and threw them back and did that over and over and over for every possible sample of size 20 we could get, that the distribution of those sample means would be normal. So we're going to use our second VARS normal CDF. So I'll scroll down to normal CDF, enter. Now we want to know that We want to know the probability that this sample mean is 175 pounds or more. So we shaded in our graph and we put in 175 as our lower bound. Our upper bound, well, we want to go up forever because we say 175 pounds or more. The mean of our sample distribution is the same as the mean for the population, 172 pounds. Here is where things get a little bit different. We know the standard deviation for the population is 29. But we are not looking at a probability for a randomly selected person from the population. We are looking for the probability involving the mean of 20 randomly selected people from the population. So we take that population standard deviation and we divide it by the square root of the sample size. Now, I like to put this in here exactly. That way I don't have any rounding error when my graphing calculator calculates the probability. If you wanted to, you could have found that first on your main screen, 29 divided by the square root of 20. You get about 6.48. And to me, that's important for graphing the normal distribution for this sampling distribution of the mean. You could put in 6.48 here, but you would get an answer that's a little bit off. There'd be some rounding error, but it's up to you. All right, so enter, paste that onto the main screen. For those of you who don't have a calculator that prompts you, make sure that you have in your notes what to put. Normal CDF and then lower bound, comma, upper bound, comma, mean, comma, standard deviation of the sampling distribution, or standard error of the mean, which is the population standard deviation divided by the square root of the sample size. Go ahead and hit enter, and here is the probability that the mean weight of 20 male passengers on a water taxi is 175 pounds or more. As always, if you have any questions, let me know. Alrighty, we are going to use our TI in order to find a percentile for a normal distribution. The normal distribution we are working with is the distribution of the sample means for the mean lifespan of tires. We have a manufacturer who's created a new tire, and the manufacturer claims that the mean design life of all of these new tires is 38,500 miles with a standard deviation of 2,500 miles. We want to take a sample of 5 tires and find the mean. And the question we are asking is, what mean would be unusually low? In other words, what mean lifespan for these sample tires would separate the lowest 5% of the mean lifespans from the rest, the upper 95%? That lowest 5% of sample means would be means that are unusually low. This mean or below is unusually low. Any mean above that is not unusually low. So we are going to go back to our distributions button. So second vars takes us to our distributions because we're dealing with a normal distribution. However, we are not finding a probability now. We are finding a percentile. A percentile is a data value that gives us a certain probability. So that is the inverse norm. Go ahead and go down to inverse norm. And here, the area that we are looking at is our percentile as a decimal. We are looking for the 5th percentile, the mean that separates the lowest 5% from all the rest. 5% as a decimal is 0.05. The mean for the sampling distribution, or the distribution of the sample means, is the same as the population mean. So the population mean, the mean lifespan for all of these tires, is 38,500 miles. Now, we need to find the standard deviation for this distribution of the sample means. We know the standard deviation for the population of all tires, that's 2,500. However, we are not looking for a percentile for an individual tire. We are looking for a percentile for a mean of 5 tires that we take as a sample. So we would take our population standard deviation and divide it by the square root of the sample size. We are taking 5 tires for our sample, so the standard error of the mean, the standard deviation of the sampling distribution of the means, is the population standard deviation divided by the square root of the sample size. Now, again, I like to put this in exactly into my calculator to avoid rounding error. If you wanted to, you could do this 2,500 divided by the square root of 5 on the main screen, and I think you get 1,118. That's important when it comes to sketching the normal distribution curve that can help you visualize what's going on. But you're going to wind up with an answer that's just a little bit off. All right, go ahead and paste that onto your main screen. Again, if your calculator doesn't prompt you, make sure your notes include how to set up these parentheses. Inverse norm, percentile as a decimal, population mean, and then whatever standard deviation you're dealing with. If you're looking for a percentile for a population, what is the data value that separates the lowest percent of all data values? Then you would just do the 2,500, the standard deviation for the population. If you are looking for a percentile for the sample means, what is the percentile, or what is the data value that separates the lowest 5% of sample means of a given size? Make sure we have population standard deviation divided by the square root of sample size. All right, go ahead and hit enter. And here is our data value, where our data is the mean of a sample of size 5. This data value, a mean of 36,660 miles for the lifespan of a sample of 5 tires or lower, is unusually low because only 5% of the samples should have means that are 36,660 or lower. As always, if you have questions, let me know.